that we take the image we get from the camera, and then we run it through a threshold. So, okay, sorry, I forgot to mention something crucial, which is that around our camera there are giant green LED rings. So the retroreflective tape around the goal appears to the camera as a glowing green hue. Does that make sense why that works? Because the retroreflective tape takes the light that's coming basically from the camera and puts it directly back in. So that way, no matter where you are in the field, there's a giant glowing green target for you to look at. Okay? So the first thing we do is we take a threshold to it. So basically, we ask the program to ignore everything that isn't green, isn't saturated enough. So saturation is, if you don't know, is how much not black or white it is, essentially, how colorful it is. A very low saturation green, for example, would be like kind of washed out, but a high saturation green, like the one in the images from the camera that you can see, are very high saturation, really bright. So we look for high saturation, and then specifically green, and then generally high intensity. So the threshold uses three values: hue, saturation, and value. So those are the three I talked about: the green, very saturated, and bright. Okay, so this is the kind of the pipe. Anybody not familiar with LabVIEW? Probably a lot of you are not familiar with LabVIEW. So essentially, the concept is that data flows through wires. So and it goes from block to block. So I'll just kind of run through it. You can ignore a lot of this, actually. So this is the threshold block. So it takes in three values which we give it, which are the upper and lower bounds for each of those three components: hue, saturation, and value. Right. So for example, we give it a value for hue from 69 to 133, which is some kind of green range, right? And it changes with the lighting in the arena. So you have a large range. It's not just a single green value. So that makes sense. Anyways, so then once we run it through the threshold, it becomes a black and white image where the white pixels are the ones that pass the threshold, that are the green, and the black pixels is everything else. So that way we get a couple of blobs, right? And so most of them are going to be U shapes, right? The target, but there are a few that are just random dots. So the next block here looks rather for the three largest particles in that the image it gets from this threshold. So a particle is like a continuous blob of pixels, right? And then it outputs a couple, and by a couple I mean a lot of different attributes. So percent area for image area is how much of the image that blob is taking up. The area is literally just the number of pixels, right? Convex hull area is the area that it would occupy if you like put a rubber band around it, and then you just fill in the inside of the rubber band how big that is. And then the bounding rectangles for the rectangles that enclose it, right? Kind of makes sense what I'm saying. So the next block scores each particle, each of the three particles that are available, based on how close they are to a perfect target. So, for example, this first block at the top here looks at the percent area versus the convex hull area. So the perfect target, right, has a certain percentage of it filled, right? If you just like look at it, there's a certain percentage that's filled because there's a huge chunk taken out, right? So the closer the target you're looking at, the blob you're looking at, is to the perfect target, how it looks, right? The more likely it is that's what you're actually looking for, right? The next one looks at the aspect ratio, the next one down. because the target is a very specific aspect ratio because you know the dimensions, right? And then the moment of inertia. So then you go, why are we talking about physics? So the moment of inertia is calculated like it is in physics, where the mass, right, where each pixel is just one mass essentially, is calculated with the distance from the center of the shape in order to determine the moment of inertia, right? And then that's compared to a perfect target. The final block is a little bit kind of convoluted. It looks at like the rows and columns and compares their average intensities to that of the perfect target. So like, if you did, for example, this year it's U, right? So if you looked at the bottommost row, you'd see a very high intensity average, right? But then the topmost row, you'd see kind of a low one because it's bright, dark, and then bright again, right? So again, you just compare to the perfect target. Okay. So you may say, how did you figure out like all this stuff? So actually, there was an example included with LabVIEW that showed how to score the target for this year because these people had WPI put a lot of thought into how to score the target. But this is an example. Basically, they did all the work for me in terms of scoring it and how to look at it. They know a lot more about this than I did, so I learned from them in how they scored it because they know of very many ways to compare these particles, right? Please interrupt me at any time if you're confused or like you need clarification on something, because I'm just talking.
So basically, you had 3 or 4 different parameters, and it looked at it from 3 or 4 different perspectives to compare to the pattern.
What she's just said makes sense to me. So now, going back to the threshold for a moment, you might think, well, how do you know where or what to threshold, right? How do you know where to set those values that I was talking about? There's a handy thing included with LabVIEW called the NI Vision Assistant. And it allows you to set up these steps kind of in a similar way like this. Not this, but this. It'll give you a VI, which is this little subroutine block, right? That contains all those steps in sequence and then outputs an image at the end. I've modified it a little bit to fit my needs better, but it's incredibly helpful, especially by the fact that you can run images through that process as you're developing it. So you kind of pretend you have this VI already, and then you put an image in and you get an image out, and you can see what it's doing. So you can run this threshold and then just screw with the sliders and figure out what highlights what you actually care about in the image, which in this case would be the target block. Right? Okay. So then once it gets the scores, I believe it compares them to a minimum score threshold. That's this blue thing down here.
We had somebody who was raising their hand.
I'm sorry.
What is VI?
A VI, okay, it stands for virtual instrument. It's this subroutine block. So like, so in here, you see this block here? Mm-hmm. This is my vision like processing VI. So essentially, in goes the image, which is this purple line, right? And the hue, saturation, and value ranges, and various other things that have to do specifically with the robot, right? And then it outputs then an image, which is basically the same as the input image actually, and then the sorted particle scores from highest score to lowest, right? Did that answer your question? So VIs have inputs and outputs. They're sort of like functions, except not, because they can have multiple outputs. So you guys understand what I'm saying? So then once, actually for our purposes, when I was thinking about how the drive team was going to look at this and understand it as the robot is doing something, I don't really want them to just kind of look at the camera image and go, gee, there's a box, I wonder if the robot's tracking it. And then the robot does something, they don't know if it's done, they don't know what's going on, right? So you kind of want to tell them. So this block here is label block. I won't go into it because it's just a lot of crunching numbers and how to draw the line exactly where I want it. But I take, for example, the bounding rectangles for each of the targets that I've detected, and I draw them around those targets on the correct place on the image. So essentially I get the image, I process it, and then I figure out what I actually care about, like I separate the targets, right? And then I put a box around them, and I color it based on which one's largest, which usually means it's the closest. That's the assumption we're under, because they're all the same size and absolute size, right? So from our perspective, the largest one is the closest one, which is the one you want to shoot to. So I color that one green, for example. And then when it's done tracking, which I know because the robot will send a message back, which I'll talk about in a minute, that says, I'm done tracking, and then it goes, great, and then it changes, like, in the middle, there's a little red X, and it changes to green plus. And it may seem kind of stupid, right? It's like kind of superfluous, but in reality, when the drive team is driving, they're under high stress, they just, they say track robot, and then it does the thing, and then boom, it's tracked, and then they know, and they can just act on that information as opposed to being totally blind. So
like a video game.
right, exactly. Lock on, established. Right. So anyway, once I get these sorted particle scores, actually to send it to the robot because it's programmed in Java, I have to turn it into an array, which is kind of a technicality, but it's important nonetheless. LabVIEW has this concept called clusters, which are just different data types shoved into a blob, right? So you can have like a string and a numeric value and a character and all kinds of things. You just shove them into a cluster and just have it spread out at the other end in LabVIEW. So for example, this right here is a cluster. I just hit Control H, this gives me a context help. So you can see here that this is a cluster of a lot of things. So it's actually an array of a cluster of all this random crap that I don't really care about very much, right? So instead, I index the array. This is a for loop, by the way, this block here. I go into the array, and each time I just pull out of the cluster what I care about, which is the distance, which is its estimation of distance. Again, I got this from the NI example. It's somewhat accurate. It's not super great because the angles involved kind of throw any estimate off. But it does give you a vague idea, and it correlates to the size. So, and then the center in X and Y. Now, actually, before any of this data comes out of the vision block, it's normalized. So we get the location on the image in pixels, right? So then we normalize it to plus minus 1, so that all the way to the right is plus 1, all the way to the left is minus 1, and same for Y, right? Make sense? Okay. But then that's not so helpful for the robot. So what we do then is we know that this camera has an angle of view, field of view of 47 degrees. You can look up these specs on whatever camera you decide to use, right? For our example, it's the Axis camera, and it has a 47-degree view angle. So I know that all the way to the left is 47 over 2 degrees to the left, and all the way to the right is 47 over 2 degrees to the right, because it's just a spherical line, right? So because I know that, then I can turn the location on the image into an angle for the robot to point to, which is much more helpful for the robot than the negative and positive, right? So then I write it to an array, and then I use it in the robot. So this is a network tables block. So what network tables does is the robot runs a server on it, and you guys know what network tables is? Anybody know? Okay. So just making sure. All right. It runs a server on the robot that just holds values, right? Like you have a value called Bob, and its value is 5, right? And then the dashboard can write to it, and the robot can write to it, the dashboard can read from it, and the robot can read from it. So this is how I communicate between the RoboRio and the dashboard. The camera image actually comes from a separate block, which is off to the left here, way off to the left. right here. This block in the center says vision. There's a reason it's encapsulated so much, and there's a bunch of crap going into it, but it's not important for the purpose of vision tracking. Basically, this outputs an image that is the camera's image, right? It talks to the camera and says, give me your image. The camera says, okay. Sense, yes?
So I have a question.
Yes.
You made the statement that you guys program your robot in Java, so how are you using this specifically for the vision if your program is being done in Java? I must have missed something.
So the LabVIEW program on the computer, you guys know what the dashboard is, right? Okay, this is the dashboard. So this program on the computer is written in LabVIEw. The code on the robot is written in Java. Network tables works between languages. Because it literally runs a server, which I'm not sure what language it's written in, but the protocol they use, I'm pretty sure
So
they
the
just...
protocol transfers from one to the other.
Right, I'm pretty sure they just send the data over UDP.
Okay.
Just with packets, right? And then if it misses a packet, it doesn't matter because it's storing the data locally on the robot. So, in any case. So I just write it to network tables and then the robot can access it, all right? I also do something here which is set new frame to true, and that's just so I know that the camera, or the PC has processed a new frame, and that the robot should know that it has new data to do something, right? And I'll explain why that's important in a moment. So, we're done with the dashboard. So does everybody understand how I process the images and get the data out of the image and then send it to the robot? Everybody got that? Nobody confused about anything, really? Because that was a lot of stuff. Sure? You won't get minus points.
So you're giving us how it runs, but just not taking us step by step by step through each little box, or did you do that and I just missed it in the first?
Okay, so it gets the image from the camera, right? And then this wire represents that image, okay?
So pink is the image?
It's actually purple, but yes. The pinks are strings, that's why I say. Yes, the purple wire is the camera image, right? This goes into this vision processing VI, right? Which then does all these operations on it. It actually makes a copy so that it doesn't affect the original image, so that I can display it later. But it goes through all these operations like the threshold, so it gets the black and white image, and then it goes through and finds the 3 largest particles, the 3 largest blobs, right? And then it scores them based on how close they are to an ideal target, right? Okay, and then I take the blobs that are now ranked by score, and I give, actually I didn't mention this, but I send all of them, all particles that I find to the robot, and the robot can determine what it wants to do with those. So it's an array of 3, it's actually a 2-dimensional array, so it's 3 entries this way, maximum 3 entries this way, and then 3 entries this way. There's distance, X and Y, right? All right, so, okay, everybody good with dashboard now?
Oh, what's the difference between this and like the other project that you have with
This is within that project.
Okay.
Okay, so essentially, you see all these things on the side here?
Yeah.
Okay, these are all outputs to this block, and then all the ones over here are inputs, like this one and this one, and actually this one too. But so then when I go to this part, right, you can see that this block has a couple of outputs and inputs, and they're the outputs and inputs you saw just a second ago. Does that make sense?
Yeah.
It's just a way to, because I could write all that code right there. It's just that it would be ridiculous to look at and like impossible to find anything. So just shove it in the box so you don't have to look at it. Okay. Yes.
Did you say that was like a given template already for this entire vision mapping, or did you have to do it all from scratch?
Okay, so the template I was talking about gets an image, and then like a predefined image from a camera, and then does these vision processing steps on it, right? That's just that block there. The rest of this, well, okay, and I modified that block to fit my needs better, like to put the box around. They didn't have that in the original, right? In their example. But the rest of this is my code. So for National Instruments examples, you go the getting started window, and then you now there's here we go. Find FRC examples. So like you click this, okay, and then you wait forever, there's a little or for it to not open at all. In any case, you can basically, oh, there we go. All right, so you just go, vision. Okay, and then it'll give you a bunch of random things you don't really care about, and then you kind of look more carefully, and you go 2016 vision example, and then you go, no, I guess you just go. And then you open it, and then, okay, it's not working. All right, should work if you installed it correctly. I installed this yesterday, sorry. You double click it, you open it, you look at it. It's an example of how to track this year's target, right? So in this case, it was doing all those 4 comparisons I talked about the aspect ratio, moment of inertia, and all that kind of stuff, right? The rest of the code that gets the image from the camera is actually, it's not very complicated. I made it more complicated because there are actually 2 camera images here from 2 different cameras. And if one of the cameras is offline, then it makes the other one like ridiculously slow. So there's a lot of infrastructure in the code here to make it so that that can't happen. Because otherwise, if our intake camera, which is just the one in the front of our robot, just fails for some reason, then we can still track the goal, right? Which before, if the intake camera failed, we just wouldn't be able to do anything, and that was not acceptable. Anyway, so yeah, there's lots of infrastructure there to do that, but just for vision tracking purposes, it's just that block that I showed. Okay, maybe I've never got it now. Okay, so now I'm going to close the last view. So we're done with that. So okay, so now that you kind of know everything about how this grinds the data and then outputs a value, you can kind of just pretend it's not even there, and that you just now you're thinking from the robot's point of view, right? So dashboard has a value for you, and it means where the targets are, and now you're going to point at them, right? That's all you have to think about now, right? You don't have to think about how it figures out where they are. You just, I know what the targets are.
All the complicated programming compacted into one basic
Right.
system.
Encapsulation, right? So now we're going to go to Eclipse, okay? Who's not familiar with Java? Okay, quite a few. All right. Notice that it's kind of the opposite of who wasn't familiar with that. Okay, so, all right, where to start here? Let's check these.
Hi, are the workshops here? Yes. Are you guys
So,
change the sign, sorry.
I wrote okay, so in Java you can write classes, which are essentially blueprints for objects, right? And then you're going to go, what the heck you're talking about? And I'm going to say it doesn't quite matter right now because I'm not going to talk about objects. Instead, I'm going to talk about static classes, which only have methods in them. So method is like a function. It takes arguments and then outputs a single value, unlike a LabVIEW. And so in this case, I've written a bunch of static methods to help me talk to the dashboard over network tables. You can use network tables directly. It's in the WPI libraries, but it's kind of irritating. You have to remember path names and all that kind of thing. So instead, essentially, the commands they had confused me, so instead of having to remember how to use it every time, I just wrote my own thing to kind of, again, encapsulate it, so I didn't have to worry about it. So in this case, I'm just grabbing a value from data vision done, which actually, if I still had LabVIEW open, you would know is that Boolean I set right at the end, actually, if you remember that. And so this is a case structure. So while I'm tracking, right, it comes in here. Okay, actually, let's start over. Okay, So the basic idea for how the robot is going to use this information is it's going to get the angle, right? Because we transformed it in the dashboard. It's going to get the angle from where it is to the target. So, does that make sense? Okay, anybody else have any question? No, you got it? All right. Okay, so now back to wasting time. So one of the things we do as well with the turret is we actually compensate for the movement of the drive base. So actually, I believe this is something that, yes?
Like a gyroscope.
Yes, well, yes, yes. If it were sitting on a gyroscope, like a gyroscopic kind of deal, that would be ideal, actually. But we don't have a giant spinning wheel of death. So instead, we don't have to wait for that, right? So instead, we have a gyroscope sensor, right, on the base of the robot. It'd be better if it were on the turret, but that requires more wiring. I don't know if you've seen the giant ponytail of wires coming off of our turret. It doesn't need any more thickness to it. So the sensor's on the base. Okay, so then we know where the drive base is pointing. So then, let's say the drive base turns 90 degrees to the right. So then, what does the turret have to do to stay pointing in the same direction?
90 degrees to whatever direction.
To the opposite direction, right, to the left.
To compensate for the
Well, could we just stop it? Right, to compensate, yes. You just go over to the robot now? I'm okay. This is the practice robot, so it's
I see the ponies there.
So there's a turret that I was talking about this whole time. So the camera used to be at the front where you just grab the turret, and now it's on top of the hood. So, well, it's not on there, obviously. It's empty, sorry. There's a drink fountain outside. Yeah, so then we take the heading of the gyroscope, essentially, and we subtract it from the heading that we initially had that is relative to the field, essentially. You say, I want to point 0 degrees relative to the field, and then you subtract the gyroscope heading of the drive base. So let's say you want to be pointing at 0, and then the drive base rotates 90 degrees to the right. So then you subtract, you now want to be pointing here. So, but this is the actual encoder reading, right? This way. So then you subtract 90, so you're pointing.
So compensation.
Right, compensation, exactly. I think they do this in places like, in certain armored vehicles, right? In like the US military, they have like a gunner, right? And he's separate from the driver. The driver's in the front, the gunner's like on the top, you know, like a Humvee, right? And the gunner wants to point that way at that guy over there that's trying to kill him, right? So he points that way, and then the driver decides to take a sharp left. So then he goes like this, right? Except they have built in, I believe it's actually a gyroscope, like you were suggesting.
So
But
that way when the driver takes a sharp turn,
he's still pointing in the
gunner's
same
still
direction.
pointing at the same.
And you can shoot that, and then he doesn't get shot. So, anyway. So it's the same idea of compensating for essentially another person causing problems for you by changing the direction you're going, right? So in our case, there's a driver, and then there's an operator. So the operator doesn't have to worry about it anymore. The operator just goes, I want to point generally that direction. That's where we're going to be pointing to shoot the goal when we get over there. And then the driver goes all kinds of, figure eights and crap, gets a ball, whatever, goes over the defenses, and they're pointing in the right direction. Just happens. Right? Actually, because we have that tether, we actually have to rotate around so that we don't break it. Actually, the tether doesn't break, the motor just stalls. But, so we can avoid wrapping the tether around the robot. I have it so that if it goes past a certain point, the rotational freedom of the turret is actually, if this is forward, it can actually go 180 and then a little bit more, and then also in the other direction a little bit more. And then once it passes that, it decides I'm going to spin around, and then it's pointing here, right? So it can face directly backward, but then if it tries to go more twisted, right, it'll flip around so that it's entirely untwisted. Does that make sense?
So if it starts facing this direction, instead of continuing to go, it will just flip around and go in the opposite.
Right, so it doesn't wrap the tether. Which was, I have that implemented already, but it's incredibly important to have it when you have gyro compensation, because the operator no longer is able to kind of make that decision. If the driver decides to do a 180 spin, right, the turret is going to wrap. So the operator can't fix that with gyro compensation. The idea is to have them not think about it, right? That's basically your job as a programmer, is to make the drivers not have to think about it. Yeah.
Is your vehicle arcade drive or tank drive?
Okay. But it's two joysticks.
In terms of robot
It's
programming.
an Xbox. Forward back. Okay, it's 7:20, so the session's over. If you want to ask any more questions, go ahead. But